just tell me when.
No, I think we
Okay.
can start.
Can we start? Yeah, okay. Christopher is not here, no? Ring the bell.
I rang the bell.
Ah, you're running.
Yeah.
Okay.
Is it recorded actually?
It's being recorded,
Okay.
yes.
Okay.
Yes.
Pablo, I have a quick question.
What?
Is the sign really required or optional?
No, optional, of course. No. It was because I'm not presenting slides, right?
Okay.
So I'm doing this on the whiteboard. And in case you wanted some material that could help you later to understand things better, in case you were interested, then I wanted to give you something, right? Yeah, not just the whiteboard. Yeah.
But there will be an exam now.
There will be an exam, yeah, today after lunch, yes. It will be quite easy anyways. All right, so this is a bootcamp on logic and GNNs. And I understand that the background of people here are quite diverse, yeah? And there are people who are not really exposed to logic before, perhaps, yeah? So I'll try to go slowly, yeah, in the beginning, in terms of the basics we need to understand in order to get to the results, right? So, and if you don't understand anything, I'm happy to stop and explain. I mean, if you don't understand something, just let me know, and I'm happy to explain further, okay? So first of all, which kind of graphs are we going to be considering? We're going to be considering node-colored graphs, okay? So what are these? These are tuples of the form G, B, E, lambda, where B is the set of nodes, E is the set of undirected edges, and lambda is a coloring function from the nodes to a set of colors that we call, say, 1 to n, right? So we have n different colors. Yeah? This is a parameter of the setting, right? The number of colors we allow. Yeah. So these are our underlying structures. In node-colored graphs, if you want to express properties of node-colored graphs, then you can use logic, right? And what is then first-order logic? First-order logic I will denote as FO. First-order logic over node-colored graphs. I will use the following syntax. I will use the following syntax. So the formulas here are defined as follows. Phi are the formulas, yes? And then you can say two things, two basic things. You can say that two elements, which represent nodes in the node-colored graph, are linked by some edge. This is something you can say. You can also say p sub I of x, where I is less or equal than n. So what this means? It means that the node that will interpret x has color I. Yeah? So for each color, we will have a unary predicate. For each color I here, we will have a unary predicate p sub I. Yeah? That tells me whether this node has this color or not. Yeah? And then we can say that that the variables representing two different nodes, the nodes representing two different variables are indeed the same variable, the same node. Yeah? These are so-called the atomic formulas. These are the basic formulas from the language. Yeah? And then you have the inductive formulas. What we can say, well, if phi is a formula, then the negation of phi is a formula. The conjunction of two formulas is a formula. Yes? So these do not need to be equal, right? It's just a way to represent it. Yeah? And finally, I can say that there exists an element x, a node in the graph, that satisfy the formula phi. Yeah? These are all the things that I can say in first-order logic over node color graphs, right? So, yes?
So x equal to y doesn't mean that they have the same color, or it does?
No, it doesn't. It means that they are the same node. So in particular, they will have the same color, right? Mm-hmm. So it is much stronger condition. This is a relation. This is a relation. This is a relation, right? But this is a very specific relation because it's the identity relation, right? So this is what you can express in first-order logic over node color graphs, right? So we will write, G satisfies phi to denote that the node color G satisfies the property phi. Okay? So let's look at this syntax here. You can have formulas that have free variables. For instance, this formula has free variables, right? But once you start using quantifiers, you can close all free variables and have something that is a sentence, right? That it doesn't have free variables anymore. When this phi is a sentence, doesn't have free variables, we can say that phi holds in a graph, right? It's true in a graph. And I'll give you some examples for this because to define the syntax is a bit cumbersome. It doesn't provide much insights. I think that an example is much more clear. Examples. This formula here doesn't have any free variables, right? All variables in the formula are quantified. Yeah? So it expresses a property of graphs, of node color graphs. Which property does it express? It expresses that there exist three nodes, yeah, X, Y, and Z, that are all linked to each other. Yeah? Every pair of these nodes is linked to each other. And one node has color 1, one node has color 2, and one node has color 3. So it expresses the property that there exists a triangle in the graph with three different colors. Yeah? So some graphs satisfy this property and some graphs do not. Yeah? And we're interested in understanding which properties can be expressed with formulas in this logic, which properties of graphs, right? This is one property you can express. Okay, here I'm cheating a bit because I'm using a Boolean connective that I didn't define here, but Boolean connectives can all be expressed in terms of each other once you have negation and disjunction, right? So what is this formula expressing? This formula is expressing that there exists a node in the graph such that for every other node, or perhaps not other node, for every node, yeah, if this node is adjacent to X, then it is not color 1. So this property is true of those graphs that have a node that is linked only to nodes that do not have color 1. Yes? Is it clear? Okay. Yes? We cannot quantify our colors. Yeah? Colors are given to us. So we can mention properties. We can define properties in terms of colors. We can only quantify over the nodes of the graph. Yeah? And this is why this is first-order logic instead of second order logic, let's say, in which you could say there exists a color relation that satisfies something. Yeah? So for instance, if you could quantify over colors, you could say that the graph is three-colorable, no? You could say that there exists a partition of the nodes of the graph in three colors in such a way that two adjacent nodes receive different colors. Yeah? This logic is much weaker, and actually everything that you can express in this logic, in first-order logic, it's not only in polynomial time, but it's in a very low complexity class within polynomial time that it's AC0. Yeah? So the properties of graphs, every property of graph that I can define here, I can check in AC0. So I cannot do NP-complete properties like the one, or like the three-colorability one. Yeah? And then a last example, theta. Okay, what this formula theta is expressing, it's expressing that every node, for every node in the graph, there exists two nodes, y1 and y2, that are linked to x, yes? They are different, and they're both color 1, right? So this is true of those graphs for which each node is linked to at least two nodes that are colored 1. Yeah? So these are the things that you can express in first-order logic. What you cannot express in first-order logic, for instance, whether the graph is three-colorable. What else you cannot express in first-order logic? There is no way I can check whether the graph is connected, for instance. Yeah? Because I'm only looking at some locality of the nodes. Yes?
Can we say or not say to how many y nodes? And I'm looking at the last formula.
Yeah.
We cannot say how many y's of the same color x cannot be connected.
There is no way you can say that. You can express this in some more expressive logics that are related to some versions. I'll try to get there. But these are the things that first-order logic doesn't have counting properties, yeah, like non-trivial counting properties. You can say there exist two nodes that are linked. You can say there exist three nodes, yeah? But you cannot say there exists an even number of nodes. This you cannot say.
Or more than two.
More than a fixed number, you can always say, yeah. But you cannot say there exists an even number of nodes that satisfy a property, and you cannot check recursive properties of the graph in terms of things that are arbitrarily far from your node, yeah, like connectedness, right? This is something that we cannot express. Yeah? Okay, so if we have a formula with a single free variable, yeah, that we denote in this way, phi has a single free variable that is x in this case, then we write G, the node color graphs, G satisfies phi of B to say that G satisfies the property phi when x, the variable x, is interpreted by the node B. Okay? So here is an example. This formula has a free variable, no? X. the variable x is not being quantified. Yeah? So it's free. So this formula, we cannot say that this formula is true or false in a graph. What we can say is that it becomes true or false once we interpret x with some node. Yeah? So which nodes satisfy this formula? Those for which every adjacent node is colored 1, right? So some nodes in the graph will satisfy the formula, and some nodes will not. Yeah? So essentially, this formula is defining a unary relation, a unary property on a node colored graph, right? And if phi, sorry. If phi x is an FO formula, and G is a node color graph, then phi of G is the set of B's, of nodes B, such that G satisfies phi of B. Yeah? So this is an important notation. If I have a formula with a single free variable x, and I have a node color graph G, I will say that the application of phi on G defines a unary relation over the set of nodes. Those nodes that satisfy the formula when x is interpreted as B. Yeah? So this is the unary property somehow defined by this formula on node color graphs. All right? Any questions so far? No?
And phi of G can be empty.
Phi of G can be empty, yes.
If no node
It can be the complete, it can be the full unary relation, it can be empty, it can be empty, yes. I will switch to another marker. So we want to restrict the number of resources that we use in first-order formulas. And a standard and very important way to do this is by restricting the number of variables that we allow in a formula. The number of variables that we use in a formula is somehow a quantification of the number of resources that we need to express this property. Yeah? So for instance, if we go back to this example, yeah, to this example here, both phi and theta are in FO3, right? We are using 3 variables to express these properties. Yeah? While psi is in FO2. Yeah? This formula here is only using 2 variables to express the property. These formulas are using 3 variables. But of course, you're not so much interested in how many variables syntactically I'm using to express this property, but whether I can express some properties using less variables, right? Yeah? If there exists an equivalent formula that uses less variables that can express the same property. Yeah? So look at this formula. I have the following formula. Exists x such that for all y, e of xy implies there exists a set such that E of Y set and P1 of set. This formula expresses something, right? It expresses something. There exists a node such that every node that is adjacent to it has some adjacent node that is labeled 1. Yeah? How many variables are we using there? 3. X, Y, and Z. But we can rewrite this formula with fewer variables. Yes? This formula is actually equivalent to this one, no? And this is one of the interesting things in first-order logic, that you can reuse the variables, right? I can use X twice in different ways, right? I can use X to refer to this appearance of X here, and I can use X to refer to this appearance of X here.
And
Yes?
the two X are not the same.
No, because once you say there exists an X, it has nothing to do with the variable itself. You're saying there exists an element, right? But I can reuse it because this appearance of X here disappears here, right? This formula doesn't talk about this X anymore. So instead of saying there exists a set, I can say that there exists an X, right? Yeah, and it's expressing the same thing. Yeah? So I'm expressing the same thing with fewer variables.
It wouldn't pass the code review.
Huh?
It wouldn't pass the code review because it creates additional ambiguity for the reader how to parse that those X's are different.
But we never showed this to the reader. This is hidden in the appendix. No, it's just an artifact to understand how many variables, how many resources you need to express a property. Yeah? But this is not a general phenomenon, right? For instance, neither phi nor theta are in FO2. Well, they are not syntactically. These formulas here, I'm checking whether there exists a triangle with 3 different colors. Yeah? Is there any way in which I can express this with fewer variables? There is no way, right? So I'm really using the 3 variables in a very essential way here. Yeah? And finally, in this introduction to logic, we have so-called counting quantifiers. If you think about it, the existential quantifier here is saying that there exists an element that satisfies phi, right? But you can have different quantifiers, no? You can say there exist 2 elements that satisfy phi. There exist 3 elements that satisfy phi. Yeah? Well, why don't we have that in the logic in first order itself? Because to say that there exist 3 elements that satisfy phi doesn't add any expressive power, right? You can say there exists x1, x2, and x3 that satisfy phi, and x1 is different from x2, and x2 is different, and so on, yeah? Why do we want counting quantifiers, on the other hand? What is the difference? Here I can say there exists two x that satisfy phi of x, right? Well, I can say that in the logic, but if I say that in the logic, what will I increase? The number of variables, right? So the beauty of this is that I can say that there exists any fixed number of x that satisfy a formula without increasing the number of variables. Yeah? And that's why this logic is powerful, not because it increases the expressive power, but because it increases the succinctness of the logic somehow. Yeah? So for instance, we have this formula theta here, yes? So it's saying that every element has two different neighbors that are labeled 1. We cannot say this with two variables, but we can say this with two variables if we allow for counting quantifiers. The way you do it is by saying for every x, there exists at least two y's that are adjacent to x and have color 1. Yeah? So by allowing counting quantifiers, we can express this with only two variables.
So there is an equivalence relationship between formulas here, subtended in your explanation, right?
Yes.
And
Yes.
is that something that can be formally set up? I mean,
Whether when two formulas are equivalent?
yes, or like
Yeah, for every node color graph, imagine that the formula has one free variable. Yeah? For every node color graph, the interpretation of the formula on this node color graph equals the interpretation of the other node color formula.
and is there an algorithm that should tell me?
No. In general, no. This is an undecidable problem.
Well,
Yeah.
it
Uh-huh.
depends whether he meant for FOK or for
Yes,
FO.
yes. I mean, there are subtle differences there depending. For instance, for two variable logic, things are very robust. But once you move to three variables, but it depends on the problem, and yes. But in general, no. Yeah. So if I ask you, given this formula with k plus 1 variables, whether it can be rewritten with k variables, this is an undecidable problem. No?
So why are we so interested in minimizing the number of variables?
We are not, well, people have looked at this as I said, as a resource, but we are not interested per se in this resource. We're interested in connecting this with graph neural networks, right? And it happens to be the case that graph neural networks are related to things that you can express with two variables. Yeah, so that's the reason. Yeah, but when you say it can be expressed, it doesn't mean syntactically. It means semantically, right? It doesn't mean that this. If you have a formula that uses three variables, then you cannot immediately conclude that it cannot be expressed with a GNN. Because it might be expressible, it might be equivalent to a formula that uses two variables, right? And this is what the result corrects, yeah?
But just to follow up, this equivalence problem for the logic you give for C2, this is decidable.
This is decidable, yes. For C2, it is, yeah. So I'm not using C2, I'm using FO2C.
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 With two variables, these problems
Yeah.
of equivalence are decidable. Yeah.
Yes.
So there was a couple questions also.
Yeah?
When you say GNN, you mean MPNN here, right? Or-
Yes. I'll define properly the model that we're going to consider. Yes?
So is it used to define whether a problem could be, a GNN could be used on a problem, or is it used to constrain the GNN?
Sorry, I cannot hear you very well.
So is this formulation used to decide whether a GNN can be used on a problem, or is it used to constrain
I'll define this formally later, but what we want to understand is what are the properties of graphs. Yeah, so we have a language to define properties of graphs, first-order logic, right? We want to understand which properties of first-order logic can be defined by GNNs as well. What is the fragment of first-order properties that can be expressed by GNNs? This is what we want to understand. But perhaps it will become clearer once I start defining these notions. Yeah? So we can come back to it. Yeah.
One more question.
Huh? Yes?
So I'm still a little bit confused by this reusing of variables. So when can we do this and when can we not?
There is, well, in the case of C2, it's when the formula is so-called counting by simulation invariant. There is a property. And this property you can check for a formula, no? That's
I thought the question was different. You're always free to do it.
Yeah.
And his comment was, you're always free to reuse variables in first-order logic.
Yeah, you can do it, but...
It doesn't always, the question is, well, can you actually get down to fewer numbers of variables by doing it, right? If you look at Pablo's example with the triangle, you can try to reuse variables. You can call it, there exists W, but there's no way you'll get down to 2 variables and express that there's a triangle.
But in general, that's undecidable.
In general, it's undecidable whether you get down, you're free to use this trick, but this trick often, as Pablo says, doesn't help you reduce the number of variables. Right?
Why it works here, for instance? It works because somehow this formula is independent from this one, right? In terms of, I can separate the variables, right? Informally, yeah? While in the triangle, I cannot, yeah?
Because they all appear together in the predicate.
Yes.
That's the point.
Yes.
I see. Okay. Yeah.
Okay, yeah, that was the question. Good.
Yeah.
Yes.
So, but on that formula specifically, the y is needed. You cannot replace it, right? Because the y is on the left is connecting the predicate on the right.
The y is needed.
Right.
I cannot get rid of the y, right? It's true. It's connecting.
It's connecting.
But this x and this x are different x's, so I can separate them. Yeah. Yeah. So once we have counting quantifiers, we can reduce the number of variables we use to express some formulas. Yeah. On the other hand, phi, the triangle, whether there exists a triangle in the graph with 2 variables, regardless of whether I allow counting quantifiers or not. Counting quantifiers are not going to help me. Yeah. So Floris, when reading the survey, asked me whether I could show some pointers to these results. And this is folklore, right? I mean, there is no single paper showing that the triangle cannot be expressed in FO2. I mean, you just use finite model theory techniques, standard finite model theory techniques to prove it. It's left as an exercise to the interested reader who never exists, right? Okay. Any questions? Because I'm going to move to GNLs now.
Can you sort of explain high level how you would prove such a thing? Like, I mean, you're saying it's undecidable, and so how do you?
Which result do you mean with the triangle?
No, so saying the phi is not an FO2. So
No. This is This is a concrete formula that you can prove that it's not in FO2 with counting. Yeah. Mm-hmm. So FO2 with counting is characterized with certain kind of combinatorial games that are called Ehrenfrau-Freise games with 2 pebbles. It's a bijective Ehrenfrau-Freise game with 2 pebbles. So you show that there are extractors that are indistinguishable by this game, and yet one has a triangle and the other one doesn't. Yeah? So it's kind of this is kind of the techniques that you use in a very, very high level way, right? So it's a combinatorial technique. Any more questions regarding the logic? No? Okay, so now I'll define graph neural networks, not because I think that you need to understand what a graph neural network is, but because it's very important for these kind of results to have a concrete GNN architecture with which to work, right? And results have different flavors depending on the different architectures that you consider. All right, so where I am? Here. Okay, so what are graph neural networks for us? Well, first of all, we will fix an activation function, yes, from the reals to itself, sigma. And we're going to define a sigma GNN as a tuple tau that contains a certain number T of matrices of appropriate dimension, A sub I, certain number of matrices B sub I up to T, and certain number of vectors, C sub I up to T. So these are vectors, and these are matrices. Yes? So if G is a node color graph and B is a node, we are going to inductively define an embedding for the node B in G with respect to this GNN. So the initial one, tau sub 0, is this tau, T, whatever, tau, yeah? Is the one hot encoding of lambda of B. Is the one hot encoding of the color of the node, yeah? So if we have n colors, we will have initial embeddings of dimension n, and we will have a one exactly on the color on the component that represents color I. Yeah. And then tau sub I plus 1 of G and B will be sigma applied to A sub I of tau sub I of G and B plus B sub I over the sum of tau sub I applied to the neighbors of B plus C sub I. So what is important here? So we use our activation function sigma. What do we use as aggregation? We use the sum. Yes? What do we use as combination? We use the sum. But we allow for a bias. Yes? So this is the GNN architecture that we will be considering in these results. Yeah? Similar results can be proved for other GNN architectures. You could use max here. You could use average. Yeah? And they will lead to different characterizations. But we think that this GNN architecture is simple and interesting enough to be studied. And that's why we started from here. Yeah? And we write tau of G and B for the value of tau obtained in the last iteration. This is the final embedding. Right? This is the final embedding computed by this sigma GNN on the graph G and the node B. Now, which activation functions will we be considering? Well, sine. The sine of x. Yeah? We will be considering sine of x, which takes value 1 if x is non-negative, and minus 1 else. Yes?
Basically, the matrices are all square matrices, or are...
No, they don't need to be square matrices. You can change the embedding in each, the embedding dimension in each layer. Yes. So you start with an embedding of dimension n, and then the first matrix can be a d times n matrix, right? And now you change the dimension immediately. Actually, this is important for the results to hold. Yeah. So ReLU. The ReLU of x is the max of 0x, right? So this function. Piecewise linear, no? And then truncated ReLU of x, which is the max of 0 and the min of 1x. It's like ReLU, but it gets truncated at 1. Yeah? Truncated ReLU. These are some of the activation functions that we will be studying. Okay, yes, question?
Is it possible to also extend this to non-piecewise linear activation functions? So how important is it that it's piecewise linear?
For our results, well, it depends on the flavor of the results. So Michael, for instance, has been studying what he calls the eventually constant activation functions. There are activation functions that have a limit on the left and on the right. And this is sufficient to obtain many of the expressiveness results. Yeah? But ReLU is not eventually constant. Yeah? And yet, some of the results hold for ReLU. So it's really, there is an interplay there that we don't completely understand at the moment. But
I think his question is also about like softmax or something like this.
Yeah, right. So exactly, like activation functions that are not piecewise linear.
yeah, softmax is eventually constant, no? It's
Yes.
It is, right?
Yeah.
Yes. And yeah, but I'll try to be very specific about which kind of activation functions we're using in the results. Okay. Okay, so we have this paper, The Logical Expressiveness of Graph Neural Networks, that I'm going to present soon. Yeah, the main result. And there is also this very important seminal paper, two papers, right, on the characterization of WL in terms of distinguishability of graphs. Yeah? And I feel that our paper is often cited because many people don't understand what's the difference between what we did and what they did, right? And I'm sure that many of you understand the difference, but I feel that this distinction is not clear in the literature. So I'm trying to make very clear what's the distinction between the two flavors of this result.
Stop citing your result. Finally.
I mean, it has not been so cited anyways. I mean, yeah, it's for my record, it's very good, but the other paper has, I don't know, 10,000 citations, right? So, yeah. But what I think that it's very important is to try to understand the difference. What's the difference between these two things, right? And there are two notions of logical expressiveness here. Yeah? The first notion is called logical, or, well, in general, GNN distinguishability, but let me call it logical distinguishability. This is logical distinguishability. This is the first flavor of the problem that is the one that is studied in these two seminal papers, right? So we have color graphs G1 and G2 and nodes B1 in G1 and B2 in G2. Yeah? And we're going to say that G1, B1, and G2, B2 are distinguishable by sigma GNS if and only if there exists a sigma GNN tau such that tau of G1, B1 is different from tau of G2, B2. Yeah? When I can distinguish two nodes in two different graphs with a sigma GNN. Yeah? This is the notion of distinguishability. So what can one prove here is the following. If sigma is any of these activation functions, the ones that we saw here, then G1, B1, and G2, B2 are distinguishable by sigma GNS if and only if there exists a GML formula, something I haven't defined, but I will define immediately afterwards, phi, such that B1 belongs to the interpretation of phi over G1, but B2 doesn't belong to the interpretation of phi over G2. So this is your well-known WL result phrased in terms of logic. Yeah? When two graphs can be distinguished by a sigma GNN, well, we know that this is the case when they can be distinguished by color refinement, yes? But color refinement also has a characterization in terms of logic. This comes from the original work of Seyfried and Nimmermann, yeah? And this says that there exists a graded modal logic formula, something I'm going to define here, such that distinguishes B1 in G1 from B2 in G2. Yeah? And the important thing is that GML is a proper fragment of FO2C. So these are formulas that can be expressed in the two-variable fragment of first-order logic with counting, but not any formula. It's a particular fragment of it. Yeah? Actually, it corresponds to what we call the guarded fragment of first-order logic with two variables and counting. Yeah? But I think that the definition in terms of GML is way cleaner. Yeah? So what is GML? And I will define it because it will play a role in the next result as well. So GML is a modal logic. Oh. GML is a variable-free logic. No, this is not working. 1 second. It's a variable-free logic. There are no variables in this logic. It's a modal logic. Yeah? And what can we express here? We can express formulas defined by the following syntax. We can say p sub I, as before, but without a variable, p sub I. We can take the negation of a formula. We can take the disjunction of two formulas, and we can do diamond. Let me check whether there is a better marker. Seems this one's better. Okay, so if G node color graph, we define phi of G as follows. If phi equals p sub I, then phi of G is the set of nodes that have color I. So each one of these formulas defines a unary relation on a node color graph. So this unary relation is phi of G. If phi is the formula p sub I, then the interpretation of phi on G is all the nodes that have color I. If phi is the negation of alpha, well, then the interpretation is just the complement, right? It's a unary relation. If phi is the disjunction of alpha of beta, the interpretation of phi is the union of the interpretations of alpha and beta. And finally, and this is the important bit, if phi diamond, don't ask me why they use this diamond. I mean, it's a modal logic convention, comes from the, 60s, 50s, something. Is this, then phi of G is the set of B's in B such that number of neighbors of B in alpha of G is bigger or equal than P. So I will filter those nodes that have at least P neighbors that satisfy alpha. Yeah? So for instance, with this logic, there is no way I can express that there exists a triangle in the graph, right? Yeah? These are the things that I cannot do. Everything that I can do here, it's actually expressible with only two variables and counting. But there are things that can be expressed in two variables with counting that cannot be expressed in this logic. What is such a property, for instance? I cannot check with this logic whether the graph has any node color 1. If it has at least one node color 1. This is something I cannot do, right? I can say that I am color 1, but I cannot check whether far away from me there is a node color 1. Yeah? These are the things that I cannot do in GML. So GML is this logic, and this is the logic that allows us to characterize when two graphs are distinguishable by sigma genus. Yes?
So if two graphs have different number of nodes, are all nodes distinguishable?
then, I mean, yes, so these will not be distinguished by a sigma GNN, right? You cannot distinguish with a sigma GNN whether two graphs have a different number of nodes, right? Because it's just local, right? I'm not doing any kind of readout or anything here. I'm just saying whether two nodes, whether I can distinguish these two nodes in these two graphs, right? So if I have a cycle and a larger cycle, no sigma GNN will be able to distinguish these two things, right? A node, a particular node. With a readout, yes. Yes?
So the logical distinguishability, and you said you want to distinguish the tuple of G1, V1, and G2.
Yes.
But what if they are isomorphic or equivalent? Let's say G1 and G2 are both triangles.
Yes. And yeah, if there is is isomorphism that maps B1 to B2, you say, there is no way I can distinguish them, right?
Right. So,
Well, yeah.
so here you implicitly assume
Yes.
that they're like
Yes.
different.
So in particular, if these are isomorphic, then no GML formula will be able to distinguish them, right?
But it's not an assumption. It's just, this is a weaker equivalence relation.
It's a weaker equivalence relation. There are things that are not isomorphic
Right.
and cannot be distinguished by this logic, and hence cannot be distinguished by sigma GNS. Yeah? Okay, so this is the first flavor of logic and GNS. Yeah? So now I will explain you the second flavor, that it's the one that we developed in this paper. Okay. And we're going to call this logical expressiveness. So to understand logical expressiveness, we need to talk about unary properties of node color graphs. So unary property of node color graphs is a function P that assigns a subset of B with each node color graph So a unary property is a function that takes a node color graph and selects some of its nodes. Yeah? It doesn't need to be isomorphism invariant or anything, right? It's just this function. It's very generic. So we're going to say that, so for instance, every GML formula defines a unary property over node color graphs, right? It takes a node color graph and it selects some of its nodes. Yeah? A first order formula with one free variable does the same. It takes a node color graph, it selects some of its nodes, right? The nodes that satisfy this property. Now, when is this expressible by a sigma GNN? Well, GNNs do not directly compute unary properties, right? Because they compute an embedding for each node in the graph. But we can easily turn them into a mechanism for expressing unary properties in this way. So we say that the property, the unary property P, is expressible by sigma GNNs if there exists a sigma GNN tau and a classification vector, CLS, such that the nodes in G that satisfy the unary property P are precisely the nodes such that when I look at the output of the GNN tau over V, and I take the inner product with this classification vector, yeah, this gives me a value, a positive value. I mean, it's completely ad hoc, the definition, right? But it's a reasonable definition. So we can take this. Yeah? For every graph, this holds. Then we say that this is expressible by sigma GNNs. And of course, there will be properties that are expressible by sigma GNNs and properties that are not. Yeah? So if a property is not isomorphism invariant, then it will not be expressible by sigma GNN. Yeah? So this is a completely different notion than the previous one, right? It's a uniform notion. It applies to all graphs at the same time. Yeah? The other one, it's data dependent somehow. I take these two graphs and I want to know when they can be distinguished. Yeah? So which properties of graphs can we detect with sigma GNNs? That's the question. Yeah? And our theorem, what it says is the following. If sigma belongs to one of these activation functions, then the following are equivalent for each FO formula phi of x. 1, phi of x is expressible by sigma GNNs, and 2, phi of x is equivalent to a GML formula. So the same logic appears in this characterization. But this notion is completely different. The proofs are completely different. Yeah? No result can be obtained from the other one. Yeah? These are disjoint results. But it's surprisingly the same logic that appears here. And what does this result say? It says two things. It says that if we have a property that can be expressed by a formula in GML, then I can construct a sigma GNN that verifies exactly the same property on node color graphs. Yeah? But it also says that the converse hold, but only for properties that are expressible by first order formulas. If I have a property that is expressible by first order formulas, and at the same time is expressible by a sigma GNN, then this property is equivalent to a GML formula. So it's a very tame formula somehow. Yeah? So this characterization holds exactly for properties that are expressible by first order formulas. Yes? Is it understandable? Yeah? Yes?
So just going back to this issue of choosing the activation, if it's just an arbitrary activation, can you say one direction, say that it's, I mean, like, are these the most expressive activations one could find, or are they?
The one direction holds regardless of the activation function that you use. So the direction that holds is like if you have a first order formula that is expressible by a sigma GNN, yes, then this has to be equivalent to a GML formula. Yeah. Now, for the other direction, we need to show that GML formulas can be expressed with GNNs. And in that case, we heavily use the shape of these activation functions, the nonlinearity. Yeah? And indeed, there is a result that says that if instead of one nonlinear function like this one, you use any kind of polynomial activation function, then this result doesn't hold. There are GML formulas that cannot be expressed with polynomial activation, with sigma GNNs, where sigma is a set of polynomial activation functions.
Maybe you could say also that if it's a continuous function that's not a polynomial, then it would be true? Like,
most likely no. Then you have to start playing with, But at least we know that if the function is polynomial, you cannot prove this result. Yeah? If the activation function is polynomial, then this result is not true. Yeah?
Question.
Yes?
Can you remark a bit more of this result and the difference between the first notion? So you mentioned this one is uniform.
Yes.
The first one is not uniform.
Yes.
But then you also said they're saying disjoint things.
Well, yeah, I don't know how to say it. What I'm trying to say is that at least I don't see a way in which one result can be proved in terms of the other. Yeah. So this is saying, take a property that is expressible by a first order formula. All the ones that I showed before, right? When can I construct a GNN that recognizes exactly the same property on graphs? Yeah? And these are the ones that are expressible by GML formulas.
Pablo, in general, I think maybe your comment is, in general, you would think of a uniform result as being stronger, but here you have the restriction to FO, which is what makes it not stronger than the non-uniform result.
Exactly. No, you're right. Yeah. I don't want to abuse this uniform versus non-uniform notation because I think that this comes from logic and complexity, and people who have been working on GNNs are not so much exposed to these ideas. But yeah, people distinguish these two results as a non-uniform flavor, the first one, and a uniform flavor, the second one. Yeah. And there is a very nice and difficult to read paper by Martin Grohe that is called The Descriptive Complexity of Graph Neural Networks, in which he presents both non-uniform and uniform results at the same time. Yeah, but it requires months of reading. Yeah, I don't understand it completely yet. Okay, what else? I mean, of course, I was too optimistic about what I was going to manage to present. But I can present a couple of things extra. Yeah, so So here we have characterized the class of first order properties, yes, that can be expressed with GNNs. And the question is whether GNNs can go beyond the FO, no? Can GNNs express properties that are not FO expressible, no? I mean, if GNNs could only express first-order properties, this would be a complete characterization of their expressive power. But it's not, because GNNs can express things that are beyond FO. What is an example? So let's take A1 to be this matrix, 0, 0, B1 to be 1 minus 1, C1 to be 0, 0 transpose, and classification vector will just be 1. So this is a single layer. GNN. Sigma can be any of those. Yes. And what this GNN is doing? Well, this is the matrix that multiplies the sum of the one-hot encodings of the neighbors, right? So it's asking whether a number of neighbors labeled 1 is larger than the number of neighbors labeled 2. Yeah, so if I apply sigma over this is checking. I mean, I want to know when this is larger than 0, right? When the number of nodes of neighbors labeled 1 is larger than the number of neighbors labeled 2. Yeah? This is not FO expressible. This is not an FO property. Yet, it can be expressed by a sigma GNN. This is precisely what, when I said that the first-order logic doesn't have counting abilities, this is the kind of things that first-order logic it cannot compare cardinalities, right? Unbounded cardinalities. So the theorem here by Michael and colleagues says the following. If sigma is sine or truncated ReLU or many others, but let's focus on these two, the following are equivalent for every unary property P. 1. P is expressible over sigma GNNs. And 2, P is expressible in an extension of graded modal logic with so-called Pressburger constraints. And what are these Pressburger constraints? It's precisely these kind of properties, right? I can do a linear combination. I can check whether a linear combination of the cardinalities of some things are bigger or equal than something. So in this case, I can do, for instance, I can check in this logic whether the number of neighbors labeled 1 is larger than the number of neighbors labeled 2. Yeah? I don't want to present the logic is not too difficult to present, but I don't think it will add to the ideas I'm presenting here. What I want to say is that this is very nice because it provides an exact characterization of all the unary properties that can be expressed in this logic. Yeah? Not just the first-order logic ones. And they can be characterized in terms of a logic. Yeah? What is the caveat? Caveat? Is that the right way to? What is missing here? ReLU. So this result only holds for what Michael calls eventually constant activation functions. Yeah? The direction from the logic to the GNN holds with ReLU as well, but the other direction doesn't hold. Yeah?
Just a quick question, but the definition of eventually constant, do you mean after a certain finite time, so the point in time, it's constant?
Yes.
Because then softmax is not.
Then it means that there exists a limit, or it means that it has to take this
It's not about
value?
Uh.
having an asymptotic limit. You require you to be constant out towards it.
Yeah, it
That's
has
why
to,
I was
yeah.
looking puzzled.
Yeah.
Okay, just to understand the definition also.
Yes, no, yeah, you're right.
So I don't know anything about the expressiveness with softmax.
I think that nobody knows anything about the
We have
expressiveness.
conjectures about what happens with regular ReLU. We have a candidate for a logic.
Sorry, can I ask one other question?
Yes.
So this actually goes back to this definition of expressible by sigma GNNs.
Yes.
Right, so typically when you do node classification, you use something like a softmax, and then or you take the argmax, right? To actually, so this construction here with getting a CLS vector, so taking this inner product, is this equivalent to being able to say something like the argmax is a particular value of, like, 1 or 0? Or?
Yeah, in this case, you just need this CLS to check whether one value is 1. Yes.
Okay, so
at least in the constructions, that's what I mean.
Okay,
Yeah.
so this is possible.
Yes.
Okay.
Yes. I mean, yeah.
Because it's kind of would be nice, right, if it was, because typically we don't do this in GNNs.
Exactly. Yes. So, yes. So you just want to check whether one element is 1. Yes. I define it this way because I thought it was clean, but you can define it in many other ways. Yes. Now, what they also noticed is that ReLU GNNs are more expressive than truncated ReLU GNNs. So it's not that we don't know whether this holds for ReLU. This is false for ReLU. Yeah? There are things that you can express with ReLU GNNs that you cannot express with truncated ReLU GNNs. And what is the kind of property? The kind of property is the following. So you have a tree like this, and here you have a bunch of yellow nodes, and here you have a bunch of red nodes. Yes, many. So a ReLU GNN can distinguish when you have exactly the same number of yellow than red grandchildren of this root. While a truncated ReLU cannot. There is no way. Because once you are at this level, yes, and you apply truncated ReLU, you are kind of clipping the numbers to become something in between 0 and 1, right? And you forget about the differences. Yeah? So that's the intuition why this cannot be done. But this can be done with a ReLU. And we have no idea what is the expressive power of ReLU GNNs. Yeah? So Martin Grohe developed an upper bound, but we know that this upper bound is not exact. Yeah? So we don't really know what ReLU GNNs can express. Yeah? Let's leave it there. I think it's a bit tiring already for everyone. And yeah, it's only 7 minutes.
We resume.
He has a question.
No, but there are questions or more questions, otherwise just go to the coffee break.
Yeah.
Kind of just, so thanks a lot. This was really exciting and super interesting.
Thank you.
So what is in your opinion, like let's say the frontier of this type of research, right? So you mentioned, for instance, that we don't know how expressive ReLUs are. So, what do you where are the big problems still?
No, I think that the most interesting problem is this softmax, then we have, I have seen no results on this direction, and yeah, softmax is something that these architectures are using in practice.
So,
right?
so mostly about the activation functions and kind of what
Yes, that's my feeling. And curiously, I have also worked on the expressive power of transformers, and in this area, exactly the same problem arises. We know very well what happens when you have so-called hard attention. You do attention, but you pay attention to the token that maximizes something, right? But when you distribute with soft attention, the expressive power becomes like very, very difficult to grasp. Yes. So I think that this is an interesting open problem. Yes.
Also the choice of agitation function.
Also the choice, but I've seen some papers in this direction, right? So if you take max, for instance, if you take max instead of sum, you cannot do graded model logic anymore, right? But you can do modal logic. Huh? You take average, then what you can do? Huh?
Since you mentioned transformers, I was wondering if sort of these kinds of results, you've done the versions for transformers, or can you say something that transformers with similar construction, like a sigma transformer, will be more or less powerful than
No, for me it's like two separate lines, so I haven't tried. I have tried to mix them in my mind, but I don't know how.
There is work on this kind of question in the transformer, but it's by different people. Right?
It's by different community, yeah.
But do we know how to relay their results to this, or is it?
Yeah, I don't know how. I don't know how. Yes, I'm not so familiar with graph transformers either, so this is something that I would have to take a look and see whether things are connected. Yeah, but it's an interesting problem. Yeah. Yeah. Sole?
What happens if you add the readout? Can you model that?
Yes. If we add the readout here, global readout, we can characterize not just GML formulas, but all formulas in FO2 with counting. So you can do things that are not guarded. That's the idea. So we can characterize. No, we cannot characterize. We can do all that, but we don't know whether it exactly characterizes. Yeah. But we can do more, definitely. And you only need one readout at the end. You don't need it in every layer. Yes. An interesting question. Interesting from a theoretical point of view, I would say. If you consider higher order GNNs, then it's not clear what the expressive power is, because you are essentially doing modal logic or graded modal logic in the product graph. Yeah? And I don't know, really. Sorry, there was a question. Yeah.
So I was just wondering whether you can change the definition to include a mod, some value, to get some range for the sigma activation values in the graph. So like to get integer values in the graph and things like that. Can you modify the original definition of the GNN?
Here?
Yes.
What would be the change, sorry?
The sum.
Here?
Yes. Mod some value to consider it as a part of a field or something like that.
Then, yeah.
I'm just wondering.
Yeah, you could do this. I don't know what, yeah. Perhaps then you can count modulo something, right? Yes. Yes.
So there is a paper on this by Bernardo.
Okay.
Bernardo's paper.
Okay.
They have a few results on this.
Okay, interesting.
Truncated sum.
All right, cool.
So what about more expressive GNNs? Do you try to do these kind of things for them, or
Which more expressive GNNs?
like the ones that I presented yesterday?
Not really. Like subgraph counting or subgraph or substructure counting. No, we have never done this. No.
Is this interesting?
Yeah, for sure. Yeah. I don't know if, what it changes from a theoretical point of view, right? But it's definitely interesting from, because it gives you a different angle. It's not just about distinguishing graphs, it's about expressing properties, right? So for instance, for distinguishing graphs, if I add a global readout, this doesn't give you anything else, right? If you add a global readout, you don't gain anything in terms of distinguishing. I mean, for nodes you do, like big cycle, but for graphs you don't gain anything. In this case, you gain something with a global readout. Yeah? So it makes a difference. It takes a different angle on the expressive power question.
Going off of the previous question, is there any motivation to sort of relate transformers and graphs, especially because a lot of people are doing empirical studies of what transformers are capable of expressing? Like there's a lot of research on mechanistic interpretability where people are empirically studying whether transformers can learn various graphical relationships to concepts, arithmetic, etc. So is there like any motivation to like use that to see like how much similarity it has with or equivalence it has with these graphical models?
I don't know. I mean, I'm probably not the most suitable person to ask this question, but the only thing that I can say is that at least for transformers, people have looked into the kind of language. It's a different problem because for transformers, you are trying to characterize the languages that you can express because these are sequences, right? So it's a formal language problem. Here it's more like a logical structure-based problem. But for transformers, they have been looking, for instance, that they cannot express parity. Many transformers cannot check whether the number of zeros in your input sequence is even or not. And they noticed this theoretically, and then empirically, they also noticed that transformers struggle to learn this kind of properties. So I think that there is an interesting interplay between what the theory is saying in this case and what we can observe in practice. But I cannot say anything smarter, sorry.
But maybe I interpret the question a little differently.
Okay.
Is in the transformer world, as you say, people have the inexpressive bound, and then they look at, can I actually express this on strings up to length 15 in the kinds of strings people might care about in practice.
Yeah.
And the inexpressively built doesn't stop you from doing this.
Yes.
And you could do the same thing here, saying, well, okay, I cannot express this property in a GNN over all graphs, but maybe up to certain lengths that I would care about in practice.
Okay, yeah.
But I don't know of any work.
Me neither. Floris.
Yeah, I was actually asked, similar to what Michael says, like, can you give up on this uniformity assumption and can we get more like conditional results on the data level, like, assuming that your graph satisfies certain properties, then we have more expressive power?
Yeah. I understand that there is a recent paper by Sami and Sami from, well, he's no longer in Hopkins, no, but yeah.
Oh, with Amita?
No, with Josue. Yeah, so they have something along these lines that I haven't read very carefully yet. So yeah, it might be interesting to do this. Yeah. Yes.
Well, marking is really a more expressive way of using GNNs. Is there like marking nodes, like specific nodes?
Like these labeling tricks somehow.
Yeah, labeling tricks.
Yes.
So is
then
there
you get
like
extra expressive power. Yes, we studied this.
Okay.
Yes. Yes, it's a different. Yes.
Sorry, what's marking?
I'm thinking about this neural Bellman-Ford stuff with labeling trick. We studied these networks, and they give you extra expressive power. Yes, but in both senses, logical distinguishability and expressiveness. Yes. Coffee.
Thank you.